Our goal for the rest of this section is now going to be to try to incorporate everything that we've done thus far to help us evaluate definite integrals, which remember you should automatically be translating to areas under curves. So in order to evaluate definite integrals, we need to know how to work with these big scary summations that we're going to generate. And so the following formulas are definitely going to be needed. What we're going to see is over here, these are three formulas that we already talked about in a previous video, so there's nothing new over here. In fact, we previously made use of this formula number 2. However, these formulas over here at the right can be a little bit, are definitely new, and so we should be able to think about what exactly they're saying. Notice what they're giving me is that a summation of the following shape can be replaced or is equivalent to each of the following right-hand sides. Now, a lot of these make a lot of sense if we just look at them very, very quickly. Notice over here, if c represents a constant, this is saying something like, if I had a summation of the value of 2 from 1 to n, then this would be a summation that looks like 2 plus 2 plus 2 plus 2 plus 2 a whole bunch of times, specifically n times, since I stopped when I is the value of n. But if I'm going to add up 2 to itself a total of n times, then what I should end up with as a result is n times 2, which is exactly what this says over here. If you add up a constant n times, then you should end up with n of those constants. That's nothing really surprising, but it just looks really confusing in this new form. Notice that over here, we can also see a rule that we made use of previously. If I notice that there's something in common, like a value of c, inside of my each of my terms, then I should be able to factor that out. We did that in a previous video with the value of 8 over n to the 3rd power. You might be able to go back and see where we applied that. We factored that out of a given sum. And over here, if I have two sums, or a sum of two formulas that are being added or subtracted, I can separate that into a sum of each of the individual formulas. So we're going to go ahead and try to use all of these ideas here to evaluate this definite integral. Now I'm going to go ahead here, and at the start I like to go ahead and try to draw a picture of what exactly it is I'm looking for. It doesn't have to be the most beautiful picture in the world, but just something to help illustrate what I'm attempting to find. Again, once I see this set of symbols, I go, oh yes, definite integral. That means I'm looking for the area under this curve. So I'm going to try to sketch the curve x squared minus 2 and shade under it from -1 to 3. So let's see. X squared minus 2 would be some curve that looks like this. Right, it would have to start down at this value. Now, -1 is probably going to be somewhere in here, since plugging in -1 would not allow me to hit 0 yet. And plugging in the value of 3, I can see is going to get me a positive value, so maybe that's going to be over here. So the total area that I'm looking for is going to be all of this area between the x-axis and the function, followed by this area up here. So one thing might pop out right away. If we've drawn this picture to scale, we would expect there maybe to be a little bit more negative area than positive area, if we've drawn it to scale, but we'll have to see. So let's go ahead and take a look here at first. How do I take this definite integral and now set it up as one of those big scary limits? Okay, well to do this, I'm going to need the same things that we did at the very start of this section. I'm going to need to think about my Riemann sums and the width of my rectangles, the right endpoints of my rectangles, as well as the final height of my rectangles. So let's start with the width. Remember here that my width is calculated by first determining the length of my interval. This would be 3 minus -1, which I clearly then see is going to be a length of 4. My interval is 4 units long. And I'm going to chop that up into, remember, n rectangles, because I want to eventually let n, the number of rectangles, go off to infinity. Now, since I don't know how many rectangles I'm going to have, I'm just going to go ahead and draw in a couple tick marks in here just to help me think about what's going to be happening next. So I want to get to the right endpoint of each individual rectangle. That's what my xi star is going to represent. So I'm going to imagine that I'm going to always start at -1, the left endpoint, and I'm going to have to add over widths of rectangles. To get to the next rectangle, I have to add one width, 1 delta x. To get to the second rectangle's right endpoint, I have to add 2, and so on and so forth. So again, I can see that I'm going to need delta x, a total of I times, for the ith rectangle. So if I fill this in, this is going to be negative 1 plus 4 over n times I. This is my formula to find right endpoints. My height is then going to say, take my function and plug in my value of xi star. So in here, notice that my function is x squared minus 2. So in place of x, I'm going to put in my xi star, negative 1 plus 4 over n times I. So once all this is done, now I can say the following. I could say that the integral from negative 1 to 3 of my function x squared minus 2 is going to be equal to a limit as n approaches infinity of my summation. I goes from 1 to n, and then I'm going to have to do the height of my rectangle times the width of my rectangle. Oh boy. All right, so I'm going to have the height of my rectangle, which is negative 1 plus 4 over n times I all squared minus 2, there's my height, times my width. This is the limit that is equivalent to this small set of symbols here in the definite integral. And my goal is to calculate this limit. Now really quickly here, there may be some of you in our class that have seen calculus before, and you might be thinking to yourself, what the heck are we doing with all these big terrifying limits? If you think you have an alternative way of actually computing what this integral value is, you can use that idea as long as you can prove to me that that idea actually works. If you are unable to justify why an idea works, you should never be able to use it. That's just kind of going to be one of our basic and has been kind of one of our basic rules throughout the semester. It was the same way with derivative shortcut rules. You were not allowed to use derivative shortcut rules if you were asked to use the definition of the derivative. And right now, we don't have any shortcut integration rules. If you think you know some, you'd have to prove that they work to me first. Okay, let's go ahead and now see how we could possibly go ahead and begin to evaluate this. Well, it's going to be a little bit of work. It's a good thing we have the whole rest of the page. So let's see. The first thing that I might do here is I might go ahead and actually attempt to simplify up this quantity that I have on the inside. And I could do that just by squaring everything out. Okay, so this is going to get me, let's see, 1 minus 8 over ni. And then, let's see, I would get plus 16 over n squared I squared. And then I still have my minus 2, and then times my 4 over n. Now again, all I did here is I just multiplied out this quantity. If you need to actually take the time to write out each of these individual things and do the distributing between them, by all means, please do so. But I just went through that rather quickly. So if you need to, pause the video, do the distributing, and double check. Now, I'm going to go ahead here and continue to work with this. I can see that what I'm going to be left with now is a limit as n approaches infinity. On the inside, I have my summation. And now I'm going to have, let's see, I can combine my 1 and my negative 2 to make minus 1. And then I still have my minus 8 over n times I. I still have my positive 16n squared times I squared. And I have times this, this 4 over n here at the front, or sorry, at the back. So I'm going to now go ahead and take that 4 over n, and I'm going to distribute this in here to simplify this down as much as possible. Again, this is what I need to do if I want to evaluate this big scary limit. I got to simplify my inside. So limit n goes to infinity. I still have this big scary summation, hoping to get rid of it soon. So if I distribute this in, now I can see that I'm going to get minus a 4 over n. I'm going to get a minus a 32 over n squared times I, and plus a 64 over n cubed I squared. Okay, so this is where I'm at. Now, I can start to see from right here that some of these rules up above are going to become helpful. Specifically right now, rule number 6. Notice here that I have a summation of a bunch of things being added and subtracted together. So this says you can take the sum of each one of those pieces separately. So I'm going to have a limit as n approaches infinity, and I'm going to go ahead and rewrite this as a summation of my negative 4 over n minus a summation, oops, sorry, there should be an n up top there, minus the summation of 32 over n squared times I, and then plus the summation of 64 over n cubed times I squared. Okay, great. So if I have this, now I can think about what I can do with each one of these summations one at a time. This may seem like a lot of work, but it's got to be done. Take a look at the first summation. Actually, I think that this summation is really, really easy to work with here, because I'll notice there are no i's in the formula. So really, my value of n right now can be thought of as a constant. And since that's a constant there, I can go ahead and actually just say that if I have the limit of a constant, then I know that the answer to that should always just be n times my constant. So I'm going to just have n times negative 4 over n. First sum is evaluated. In my next summation, I'll notice that I have a constant times I. So I'm going to go ahead and I'm going to take my constant and pull it outside. Again, it has nothing to do with I, so I can treat it like a constant. I can do the same thing with my third summation, and I can pull out this 64 over n cubed. And I'm going to be left with this amount here of I squared. Now I can see that each of these quantities here is a sum of I and a sum of I squared, and I have formulas for those in formulas number 1 and in number 2. So I can go ahead, I can write this down again. This is a lot of simplifying. Let's see here, I'm going to have negative 4. Here my n's are going to cancel. Here I'm going to have a 32 over an n squared, and all of this summation of I can be replaced with an n times an n plus 1 over a 2. The rest can be replaced with, I still have my 64 over n cubed, and then the rest of this can be replaced with my n times n plus 1 times 2n plus 1, all divided by 6. Now I'm going to go ahead here and just quickly think about what's going to be happening as I try to now evaluate this limit. Notice I've gotten rid of all the summations. That's really my goal. And now I'm kind of back to a limit that I had at the start of the semester. Now notice there's a couple nice things that I can do here kind of right away. First, I can see that I'm going to have, at least at the start here, still just a negative 4. And then I can combine my fractions here to make 32n times n plus 1 over a 2n squared. Over here I can do the same thing, 64n times n plus 1 over 2n plus 1, all divided by 6n to the third. And so I can now imagine doing the limit of each of these pieces. But actually, doing the limit of each of these pieces is going to be really simple if instead I focus on an old fact that we had from early in the semester. You might recall that if I was ever going to do the limit of a polynomial, the leading term was going to be the only term that mattered. And notice here that when I have to do the limit of, say, this second fraction, I can do the limit of the top and the limit of the bottom. The limit of the bottom is going to be easy to think about. The limit of the top is, again, a more complicated polynomial. I might require to multiply some things out and simplify some things down. But since it's a polynomial, if I can identify its leading term, that's the only part of it that's going to matter. And so I'm going to go ahead here and think about writing out here the leading term for the numerator of each of my fractions, since that's the only part of the limit in the numerator that's going to matter. Notice up here, I can see that I'm going to get a 32n squared and a 32n when I distribute. So the only one of those that's really going to affect the limit is the 32n squared. Similarly over here, I have this 64n, and when I distribute all this in, I'll notice that I could get a grand total of 128 n cubed as my leading term. Now, the reason that I can see that again is notice that I'd have 64n multiplied to this n, so 64n squared, and then when that gets multiplied to the 2n, the 64 is going to double to 128, and I'd be up to n cubed. So notice then that I can go ahead and continue to work with this. I'm going to end up with now a limit here of -4. Oops, actually I can calculate these limits here really easily by just simplifying out what I have here. I'm going to have a limit of -4 minus 32 over 2 plus 128 over 6. And that's ultimately just going to leave me with -4 minus 16 plus 128 over 6. Now, if you were to simplify all of this down, you should be able to get down to a final value of 4/3. And so what is the importance of this 4/3? What does it represent? Again, this 4/3 here represents the exact area that we were looking for up above. The exact area here is 4/3. And so I'm going to go ahead and write this out in the following manner. I'll say that the integral from -1 to 3 of x squared minus 2 is equal to 4/3. Wow, okay, that is a lot of work to move through this particular example. It's a lot of work, but it's stuff that we have to be able to understand how to do. And of course, the best way to do that is with practice. So what I'm going to ask that you attempt to try to do is to take a look here at example number 6 on your own. Try to see if you can work through example number 6. Now, I won't go through the solution here in the video, but there is a very extremely detailed solution posted in the notes up in Blackboard that I'll ask you to look at. And of course, if you happen to have any questions on this example, you can by all means feel free to talk with me about it in office hours. In the next video, we'll jump ahead to example number 7 and talk about some of the important things that we'll see in that example and how it leads us into our next important section.